Hello everyone, thank you for coming. My name is Eric and today I will present you the dynamic modeling of a wing-assisted incline running with a morphing multimodal robot. This is authored by me, Ali Reza Ramezani and Morteza Garib, and we're from California Institute of Technology and Northeastern University, USA. In this work, we developed an MPC-based controller to climb a steep surface using our morphing robot, the multimodal mobility morphobot shown on the right over here. The robot is capable of transforming into multiple modes and repurpose the actuators attached to its limb to alternate between wide array of locomotion modes, such as ground in here, UAV, aerial modes in UAV, and mobile inverted pendulum mode over here, or segway mode. So here we're going to use this MIP mode to perform wing assisted incline running or WAIR to climb a steep surface. First, we will briefly explain the M4 design and key features. The robot has 4 legs, but only one leg is shown on this figure for simplicity. Its leg has 2 hip joints over here, frontal and sagittal, to rotate the leg sideways and upwards. The leg has a wheel driven by this motor over here, attached with a gear and gear mesh on the wheel itself. There's a propeller motor stored inside the wheel axles and to drive the propellers to in the UAV mode or in the segway mode. The robot weighs around 6 kilos and has a maximum thrust of around 9 kilos, so we have a thrust to weight ratio of 1.5. And the robot has 16 actuators and can be modeled using 80 degrees of freedom if we ignore the propeller dynamics. Next is the problem statement. So we want to do some bio-inspired maneuver using wing-assisted incline running as shown over here on Chukar or Hoatzin birds, that they can use their legs and wing at the same time to climb steep surfaces. We can do the same in a similar fashion with the MIP mode, using the wheels at the ground to as similarly to the legs of this bird, and the thruster at the top to use it in the same manner as the wings of the birds. In order to do so, we have to regulate ground forces so that the wheel does not slip. So this is how the bird doing it. So you can see like it's using its leg and wings to climb an almost vertical surface. And we're trying to do the same thing with our robot here. In this slide, we show some examples of other existing multimodal robots to relate our robot with. This robot can be categorized into 3 types. First one is the redundant design, where each actuator is only used in one mode, such as this ground aerial UAV that's basically a quad-rotor with wheels. So the rotor only do the flying and the wheels only do the ground modes. There's also limited appendage redundancy manipulation, where the appendage can serve multiple modes, most prominently on the wheel-triggered robots over here, where at the end of the leg is there's a wheel, so it can alternate between legged and wheeled locomotion modes. There's also the last one, the morpho-functional robots over here, where it can transform the robot limbs and use the actuators for multiple modes of locomotion, and our robot belongs in this category. So in this slide, we'll do some brief analysis on the dynamic modeling. The full derivations can be seen in the paper, but the idea is that we have a simulation model using the full model, and then we do the reduced order model for MPC. And in the reduced order model, we use a planar dynamics model shown over here, and the equations are used in the MPC equation. So this is the model, dynamic model, the reduced order dynamic model, and we have the ground force constraint over here, and we have the actuator limit, and this is the cost function used in the MPC. So we set up the simulation in Simulink real time, and we can perform this wall climbing maneuver shown over here, where the robot just goes straight into this 15 degrees angle incline and running with MPC. So this is done with Simulink and Simscape multimodal library. So the simulation plots can be analyzed and shown that it works. So the MPC over here shows that the constraint equation is satisfied, and then it tracks the desired trajectory over here. So this slide shows how the robot transformed from the rover mode into segway mode. So the robot transformed into the correct configuration and then use the thruster to lift the robot up, upright it into the upwards configuration, and then in here. Like it will do the standard segway balancing with just the wheels. And then if you want to transform back into the rover mode, you can do the reverse action by slowing down the descent using the thruster, and then like transform into the rover mode after it has safely land. So this is some examples on the experimental work we done on this climbing problem. So we have the robot in segway mode drive up this steep surface of 30 degrees. The wheels are spinning to maintaining traction on the ground, and we have the thruster on to maintain to help maintaining the correct angle as we climb this surface. This is a more steep incline of 45 degrees. As you can see over here, it cannot climb it in rover mode because it's stepping. So we using the thruster and the wheels, we can safely climb this steep surface, no problem. This wire is for safety, so in case something bad happens, but it's not doing anything as it's like relative to the robot. In conclusions, we have presented the dynamic formulation and simulation to perform a WAIR maneuver with the M4 robot in segway mode. We have presented the feasibility through experiments, and for future work, we can extend this problem into 3D, and where we don't just climb along the incline surface, but also like maybe traverse like laterally along the surface, or maybe we can also explore other optimization control techniques such as collocation and Lyapunov-based control functions. Thank you for listening and have a good day.